Hello and welcome back to my channel. In this video, I'm going to be showing you how to use ice charts. So if you've been struggling with equilibrium calculation questions that involves ice charts, then this video is for you. And don't forget to subscribe to my channel for more chemistry tips. The first question I have says, at a certain temperature, the equilibrium constant for the reaction is 38. If 1 mole of S2 and 1 mole of Y2 are placed in a 1 liter container, what are the equilibrium concentrations of all species? The first thing we do is write out our rice table. Now, I'm using the word rice because that's the full one. The R represents the reaction, okay, which is the X2 plus the Y2 to give us 2XY. I is the initial concentration. Concentration is moles per liter. In this case, they gave us 1 mole. So you need to divide it by the liters in order for it to be a concentration. In this particular question, they gave us 1 mole and 1 liter. So 1 mole divided by 1 liter is going to give us the same thing. So it's a little bit easier, okay? So 1 mole over 1 liter gives us 1 moles per liter. So our initial concentration for S2 is 1. And since Y2 also has 1 mole, that will also be 1 mole over 1 liter, which also gives us 1. Okay, 1 moles per liter. Now, initially, this was not present. I need you to understand this. It says if 1 mole of X2 and 1 mole of Y2 are placed in the container. So that's the initial procedure of adding them together. So the product was not formed at that point. So that means this is going to be 0. It's nothing, like it wasn't there at all at that point. Now, C is what we call the change in concentration. And the change in concentration of the reactants will usually be negative because the reactants are disappearing, while the product is positive because they're appearing. So you can use any alphabet to represent your change in concentration since we don't know what it is at the moment, okay? Or you use the very common one, which is X. So I'm going to be making use of X because I want to align with what the textbooks is saying so I don't confuse you, okay? So for this X2, since this is just 1 mole, like I'm talking about, this is empty, so that means this is 1, okay? It's just going to be negative X, so just 1X. You don't have to put 1 in front of the X because when we see it, we know that that is just 1. This is also going to be exactly the same because we have 1 mole of the Y2. And remember, the mole has nothing to do with the initial concentration. I'm talking about the balanced equation. You only have 1 of S2, 1 of Y2, okay? And that's why we have a negative X for those two. Now, when we go to the reactant, that will be a positive 2X because you have 2XY, okay? Now, E is known as equilibrium concentration. And equilibrium concentration would just be bringing the I and the C together. So 1 minus X for this one, and this would be 1 minus X as well. Why this is 0 plus 2X, that is 2X. So we have our rice table or ice chart set up. The next thing is to write the equilibrium constant expression, Kc. Now, some textbook will say KEQ. Some will just say K. They're all the same, okay? It depends on what your teacher loves using. The common one is Kc. So we're going to use Kc. So Kc would then be equal to the product concentration over the reactants concentration. The product here is Sy. So the concentration of Xy. Now, in equilibrium, we use this bracket to represent concentration. But because this is 2, the exponent here, the exponent is going to be 2. So you square it because it's 2 of them. So divide that by the concentration of X2 times that of Y2, okay? Now, the Kc they gave to us to be 38. So we're going to plug in this into the equation. So 38 equals, at equilibrium, our x, y is 2x. So that would be 2x squared. Okay, you just substitute over 1 minus x for the x2 and 1 minus x for the y2. Now, this is the same thing as simply saying, let me write it down here, 2x squared over 1 minus x squared. That's the same, okay? These two, you can square it. So now that they both have squares, the easiest way to solve this is to do the square root of both sides to get rid of the squares. The squares here we cancel out. And then if we do the square root of 38, that gives me 6.16 equals 2x over 1 minus x. Now cross multiply. 6.16 times 1 gives us exactly the same. 6.16 times negative x gives me this. And then on this side, you have 2x. So you bring the like terms together, take the negative 6.16s to the right-hand side, that becomes positive, or you can simply add 6.16s to both sides. On the left-hand side, that will cancel out. So you have 2x plus 6.16x. So this is going to give us 6.16 equals 8, if you add this up, 8.16x. And to find x, we divide both sides by 8.16. So I'm just going to continue on this side. So that simply gives me x equals 6.16 over 8.16. And that is 0.755. So moles per liter is the same as capital M, which is molarity, moles per liter, okay? So that's my x. Now remember, the question says to find the equilibrium concentration of all the species. So we're going to go back to this. For x2, you're simply going to substitute the value of S to this. So the concentration of S2 at equilibrium will be 1 minus the value of X we just calculated, 0.755, and that will give 0.245 molar. Now remember, Y2 is the same as well, right? So that gives us the same thing. And then the XY would be 2 times the 0.755, which is 1.51 molar. Okay, and those are the values that they want you to calculate. So this is how you set it up and how you solve it, okay? Now let's move on to the next question. For the reaction, which they gave us there, if initially SO2 is equal to 0.5 molar and NO2 is equal to 0.5 molar as well, and at equilibrium, the NO is equal to 0.3 molar, find the Kc. So we just learned how to find the equilibrium concentration in the last example. In this example, we're going to be learning how to solve for Kc. So we have, again, our rice charts. The reaction is SO2 plus NO2 to give us SO3 plus NO. Initially, this time they gave us the concentration, okay? Initial concentration. So you have 0.5 for both initially. These two were not there at the beginning, so you can just say 0 or dash. Now, this is going to be negative x, again, because the reactance is disappearing. So we're assuming that the value is x because we don't know what it is. And since it is reactant is negative. And since this is just 1 moles of each of those, it's just 1x, okay? So negative x for both. And on the product side, it's appearing. So because you are forming the product, it's positive x for both. Now at equilibrium, you add them up. So 0.5 minus x, 0.5 minus x. This is 0. 0 plus x is x. 0 plus x is x. Okay, so we have our rice charts. Now, note that it says here at equilibrium, this NO is 0.3. Now, if NO is x at equilibrium, that means that this x is equal to 0.3 because the equilibrium concentration of NO is 0.3. And that's how we find our x. So the x is exactly 0.3 for both of this, okay? 0.3. Now we know x, we plug that here. So 0.5 minus 0.3, this will give me 0.2. This will be 0.5 minus 0.3, same thing, 0.20. So we have our equilibrium concentration of each reactant and product. To calculate Kc, we first write out the expression. So that would be the concentration of SO3, the product, the NO as well. So the concentrations of the products over the reactants, SO2 times the NO2. And we just simply plug in these values. So you have 0.30 times 0.30 divided by 0.20 times 0.20. So 0.3 times 0.3 divided by 0.2 times 0.2, and that gives me a 2.25 as my Kc. Okay, that's it. That's how you calculate your Kc. The next one, it says for the reaction as given, if CH3COOH was initially 0.10 molar with a Ka of 1.8 times 10 raised to the power of -5, what is the pH of the solution? So this has to do with pH of weak acids. So I wanted to throw in this example just in case some of you are finding this problem difficult as well. So we start off with the ice chart again. Okay, so start with your reaction, which is CH3COOH dissociating into CH3COO negative plus H plus. Initially, they gave us the concentration of acetic acid to be 0.100. And of course, these two were not there. Now, change in concentration for the reactant here would be -x. These two will be +x, +x. Now, at equilibrium, this is going to be 0.100 minus x, while this is going to be x and then x. 0 plus x, 0 plus s gives us x. All right? Now, we will set up the K expression. This time we're dealing with Ka is the acid dissociation constant. Okay, it's under acid-base equilibrium. So we've seen equilibrium constant, which is Kc. Ka is also equilibrium constant, but more specific for acid. So we say it's acid dissociation constant, Ka. If you see Kb, that one is base dissociation constant. So Ka will simply be equal to the concentration of CH3COO negative times H plus concentration over CH3COOH. Now you might be wondering, why do we need to do all this? pH is equal to negative log of H plus concentration. So we need to figure out what the equilibrium concentration of this X is. And that is because this is a weak acid. Weak acid, we cannot calculate pH with the initial concentration because weak acid does not dissociate completely in aqueous solution. So you need to figure out what the equilibrium concentration is before you can calculate the pH. Strong acid, because they dissociate completely, you can calculate their pH without having to go through all of this trouble. Okay? So the Ka given to us is 1.8 times 10 raised to the power of -5, which is very small. When we have a very small Ka, we use the approximation method where we're going to ignore this -x. Okay, so The x times x here gives me s squared. So these two, x times x squared, over, so instead of saying 0.100 minus x, I'm just going to go ahead and say 0.100. And that's because the Ka is small. I have different methods of figuring this out. One of those methods is simply multiply this by 1,000. Okay? If it gives you a value that is still less than this initial, then that means that your change in concentration is negligible. So you don't have to use it. There are several other ways you can figure that out. Okay, but this is one. So you can easily just try that now. If we do 1.8 times 10 raised to the power of -5, and then multiply that by 1,000, that gives us 0.018, which is still less than the initial concentration. So once that happens, then it means that the change is really, really very small, that you can ignore it. So with that said, we're going to go ahead and cross multiply. So you have 1.8 times 10 raised to the power of -5 times 0.1. That gives me a 1.8 times 10 raised to the power of -6. And then this is equal to x squared. So to find the x, you do the square root of both sides. Okay, this will cancel out. X will then be equal to the square root of 1.8 times 10 to the -6, and that gives us a 1.34 times 10 raised to the power of -3. That is our x value. Now remember, the concentration of H plus is equal to x, and since x is equal to this, that means that the concentration of H plus will be equal to 1.34 times 10 raised to the power of -3. Okay, so all we need to do now is bring out our pH formula and plug in the value of H plus. So negative log of this value, 1.34 times 10 to the -3, and that would simply give us 2.87 as our pH. Okay, and that is how you calculate this. I hope this was helpful. Don't forget to subscribe to my channel and share to others who might find this helpful. And thank you so much for watching, and do have a wonderful day. Bye.